Just want to do a little bit on multi-level modeling. I'm not going to go too deep because it's a very big topic, but you can dig deeper if you're interested. We've talked about different types of fixed effects and factors. Multi-level modeling is basically just generalizing from those fixed effect models. Gelman and Hill have a great book on data analysis using regression and multi-level/hierarchical models. For instance, we might want to use occupation data in some wage equation, understand how much money people are making. If we didn't put in any factor or fixed effect for occupation, then that would pool everybody together. Everybody's wage would start from the same value predicted. Or you use a fixed effect for each occupation. That's the no pooling method. But while there are some occupations that are really big with lots of data points, there are others with really small number of people, relatively unusual occupations, so that fixed effect coefficient could have very large errors. We could measure any crazy values. If there are one or two people in an occupation, one outlier could drag the whole estimator around. We might want to give a little more structure to the problem to model that we expect to use the overall pooling estimate of the grand average, but as we get more observations, then we'll gradually shift the estimate. And that's what multi-level modeling is doing. Groups that are really large get nearly the fixed effects estimate, while smaller groups are going to be weighted towards the pooled value of the overall average. Let's go a little deeper into the notation. We model the wages of person I, industry J, where X includes all the other explanatory variables. With the pooling model, Wij is going to be just alpha, that's the ordinary coefficient for everybody, plus beta Xij plus the error. With the no pooling model, each occupation gets its own alpha j. Each occupation can have a different level. Wij is alpha j plus beta Xij plus the error. The multi-level model will split those alphas. There's alpha naught plus alpha j with square brackets to distinguish. We further model that alpha j with square brackets has a normal distribution with some sigma coefficient of its own, sigma alpha, describing how much variation it has. If we had only a single factor, then all this might seem a little extra, but this generalizes to models with lots of different factors: occupation, industry, geography, etc. With more and more intersecting segments, each would tend to be even smaller. Even relatively coarse occupation factors, hundreds of people in them, once we slice by geography, major, whatever, how many of them were in the state of New Jersey or majored in philosophy, means a pretty small cells of people fit all those crosswise levels. That risks having the estimators chasing outliers. Therefore, the additional structure can be really helpful. The next step is to include interactions with the slope, just like we did before with factors, but now with this additional structure imposed. Mathematics gets a little more complicated, and the estimation machinery gets a little more complicated, but we can model where the slopes can vary for different groups. To do that in R, instead of LM, we have LMER. There's a little bit of difference about how to specify the model, but it's not that complicated or difficult. You can get more accurate estimations. I won't go into great detail here, but if you want to learn more about this, and I'd recommend it, then you can do some exploration on your own.